Welcome to Tomorrow Unveiled. So if you felt like the space news cycle was moving at, well, light speed this past week,
Right.
that's October 17th to the 24th, 2025, Kenny 25, you really weren't imagining things.
No, definitely not.
Our dedicated research team pulled together a whole stack of materials, and it doesn't just point to a busy week. It feels like, well, we're calling it a generational leap. It really seems like we're watching the moment the whole aerospace industry stops just, dreaming about that beyond Earth economy.
Right.
And actually starts putting down the concrete, the steel, the industrial and tech foundation for it.
Exactly. It's not just upgrades anymore.
No, it feels much bigger.
Yeah.
Like establishing the actual hard infrastructure, finding these huge efficiency gains that just rewrite the physics of getting around.
Yeah.
And these massive strategic moves happening back here on Earth that are totally reshaping, global competition.
That's a great way to put it. A phase transition, really, not just slow evolution. When our research team kind of distilled everything down from the last 7 days, 4 big themes kept popping up. Themes that really define this new strategic reality. First, the acceleration of genuinely revolutionary propulsion, the actual engines we need to, shrink the solar system.
Right.
Second, huge strategic and industrial realignment. You see it with the big space powers, especially in Europe and Russia. They're being forced to react to the sheer speed of commercial space. Third, just the relentless maturing of orbital infrastructure. Things like refueling, computing, servicing, making LEO and that whole Cis-Lunar space sustainable, viable places to actually do business.
Okay.
And finally, we got this incredible high-stakes, real-time demonstration of deep space mission agility, which was, well, quite something thanks to a visitor from way out there.
And that's really our mission for you today listening to Tomorrow Unveiled. We want to give you the shortcut, the insight into the why. Why these specific shifts in tech and politics really matter, and how they're going to define who leads and who follows in the space economy for, well, probably the rest of the decade, at least. Okay, so let's unpack this, starting with the literal engines.
Yeah.
Things driving this future. Next generation propulsion.
Right.
The consensus from our sources, it seems pretty clear. The biggest news, maybe the most important technical validation this week, was that strategic investment by Lockheed Martin Ventures.
Yeah, into Venus Aerospace.
Exactly. Specifically for their rotating detonation rocket engine, the RDRE.
That investment, the one announced October 22nd, it's way more than just, seed money.
Right.
It's this powerful strategic nod from a huge U.S. defense prime. It basically says, okay, RDRE isn't just a cool university idea anymore.
It's real. It's hardware. Close to ready.
Exactly. Strategically critical hardware. And the significance really comes down to how these things work. It's totally different from, well, any rocket we've used for the last 70 years.
Right. Because if you think about a standard rocket engine, like the Saturn V's J2 or even the Merlins on Falcon 9s, they use deflagrates.
Subsonic burning.
Yeah. You mix a fuel and oxidizer, they burn continuously, nice and stable. It's powerful, sure, but it's fundamentally a controlled fire. A slow burn, relatively speaking.
The RDRE just kind of flips that whole thermodynamic concept on its head. Instead of that subsonic burn, it uses a continuous supersonic detonation wave.
Okay, detonation, so explosions.
Basically, yeah. Picture a shock wave, an explosion, cycling around inside this spattle donut-shaped chamber thousands of times per second.
Wow.
This standing shock wave kind of holds the high-pressure burning stuff in place for a microsecond, squeezing way more energy out than just stable burning can.
So it's like the difference between just lighting a campfire and setting off this continuous, perfectly timed ring of explosions.
That's a pretty good analogy, yeah.
Yeah.
Tightly controlled, continuous, circular explosions.
And the numbers the research team pulled out, they really show why this matters, right?
Oh, absolutely. The reports point to up to 25% greater efficiency compared to conventional engines.
Now, 25%, you hear that in business, it sounds okay. But in rocketry, with the, the tyranny of the rocket equation.
It's massive, nonlinear, huge.
It translates directly into this enormous advantage, right, in mission economics.
Exponentially so. That efficiency boost means you get the same kick, the same delta V, with way less fuel to start with. The analysis suggests it could cut the fuel needed for a trip to Mars by, potentially, a staggering 20%.
20% less fuel for Mars.
Think about what that means. It's not just saving money on propellant. That's 20% more stuff you can carry.
Right. More equipment, more supplies for the crew, better shielding.
Exactly. More life support, more redundancy. It takes a mission that's already incredibly hard and makes it dramatically more doable.
But okay, you say continuous explosions cycling inside an engine. My first thought is, how does it not just, tear itself apart?
Yes, the cat.
What are the big engineering challenges? Reliability.
That is the absolute critical hurdle. The thermodynamics are amazing, yes, but the mechanical stress is just immense. The RDRE runs much hotter, much higher pressure than a normal engine. So the main challenges are all about material science.
Finding stuff that can take the heat.
And the constant intense detonation stress. Without, failing catastrophically.
Yeah.
Alloys, thermal coatings, that's where a lot of the work is. Plus, just starting it up reliably, keeping that wave stable, it's tricky.
So they've run them for minutes in tests.
Yes. Early prototypes have shown stable operation for minutes. But turning that into an engine you can trust for flight, that can restart multiple times, burn for maybe a 15-minute insertion.
Yeah.
That means solving these really tough thermal management problems, that Lockheed investment. A big chunk is likely aimed right at cracking those material and structural challenges faster.
What's also interesting is the dual-use thing. This isn't just about cheaper Mars trips.
Not at all. This tech is absolutely critical for the defense world, especially for hypersonics.
Right, because it gets you to high speeds efficiently.
Exactly. It's a key component for next-gen hypersonic cruise missiles, maybe interceptors. That market's projected to be, nearly $12 billion by 2032?
Wow.
So having RDREs work for both defense and commercial space, that gives Venus Aerospace and Lockheed a much more stable, resilient business. They aren't just reliant on the ups and downs of space funding.
It really feels like the first genuine generational jump in rocket tech since, Apollo.
It does. And this RDRE news, it fits into this wider pattern we saw this week, a real focus on efficiency, not just raw power.
Yeah, like the other innovations mentioned.
Right. Context is important. While RDRE gives chemical rockets that 25% boost, you've also got work on things that were pure sci-fi until recently, like Ohio State University's work on the Centrifugal Nuclear Thermal Rocket, CNTR.
Okay, let's unpack that a bit.
Yeah.
Nuclear thermal rockets, NTRs.
Mm-hmm.
They're like the classic holy grail for efficiency, right?
Mm-hmm.
Why does this design potentially double the performance of chemical rockets? What's the trick?
Well, the basic limit of a chemical rocket is just how hot you can burn the fuel before the engine melts. There's a hard cap on chemical energy.
Okay.
The CNTR and NTRs in general, they just bypass chemical energy. They use a nuclear reactor core to heat up a propellant, usually liquid hydrogen, because it's light.
Fluctuating it.
Exactly. In the CNTR design specifically, the hydrogen flows through this rapidly spinning reactor core, that's the centrifugal part, and gets heated to extreme temperatures, way hotter than any chemical flame.
Mm-hmm.
And the performance gain, it comes straight from physics. Rocket efficiency depends on how fast the exhaust shoots out the back.
Exhaust velocity.
Right. Hydrogen is the lightest stuff there is. Heat it with nuclear energy, you can blast it out way faster than heavy chemical exhaust. That's where the doubling of efficiency comes from.
And doubling efficiency, that's the magic number. Because it takes that, 9-month to a year trip to Mars?
And potentially cuts it down to 6 months.
Which is just huge for the crew.
Yeah.
Less radiation, less time cooped up.
Yeah.
Lower overall cost. It changes the whole mission profile.
Completely different kind of mission, yeah. And then on a different track, we also saw news about propulsion evolving towards, not more power, but maybe greener operations, easier handling.
The impulse space lander.
Yeah, they unveiled a new lunar lander design using nitrous oxide and ethane, a biopropellant.
So why that specific combo? What makes it green or easier?
Well, a lot of the really high-performance propellants used for deep space, like hydrazine, they're incredibly toxic.
All right, need the full hazmat suits, special procedures.
Exactly. Complex, dangerous, takes a lot of time on the ground. Nitrous oxide and ethane, much safer to handle. Considered green, It dramatically cuts down the ground processing time, the complexity, the cost.
And it still performs well enough for landing on the moon.
Yeah, it strikes a good balance. Enough performance for orbital adjustments for the descent, but without the toxicity headache, which is really important if you want to make cislunar logistics, routine and affordable.
It seems like the whole field is shifting. Not just bigger bangs, but smarter, tailored energy use.
That's a good way to see it. From brute force to efficient application of energy.
And the sheer variety here. RDREs for performance, nuclear for speed, these green propellants for safer operations.
Yeah.
It really proves the point. This isn't just tweaking things.
No.
We are genuinely seeing a multi-generational leap happening right now. If you're finding this insightful, please take a moment to like this video if you're on YouTube, subscribe to Tomorrow Unveiled, maybe hit that new hype button. It helps us reach more people.
Yeah, definitely helps.
And, of course, turn on notifications so you never miss an update on what the future holds.
Okay, so propulsion gets us there faster, maybe cheaper. But infrastructure. That's what determines if we can actually stay there.
Right.
And more importantly, if we can run a real viable economy once we arrive. This past week saw some really critical progress in making low Earth orbit and that whole Cis-Lunar space area sustainable.
Okay, before we jump in, quick definition.
Yeah.
Cis-Lunar space.
Right. Good point. Basically, it's the whole area of space under the gravitational influence of both the Earth and the Moon.
So Earth orbit, lunar orbit, and everything in between.
Exactly. Including those gravitationally stable spots, the Lagrange points. They're going to be essential hubs, like ports, for future deep space missions. Think of it like it's the new ocean, the maritime zone for the 21st century.
Okay. And if it's going to be a port?
You need gas stations.
Exactly. Let's start there. The logistics problem. In-orbit propellant management. If we want to go far, we have to solve that huge cryogenic fuel issue. Boil off.
And that's where the Rocket Lab and Eta Space LOXS mission fits in. It hit some key validation milestones this week.
Right.
Its whole purpose is to prove out zero-loss storage of liquid oxygen, LOX, which is cryogenic, over 9 months in orbit.
9 months. Wow. Because boil off, it's like the silent killer for long missions, right? Fuel just evaporates.
It really is. On Earth, we just use refrigerators. But in space, keeping something colder than minus 297 Fahrenheit, incredibly hard. Current systems just aren't good enough. Fuel literally vanishes while you're waiting for your launch window.
So how are they actually trying to achieve zero loss? What's the tech?
It's mostly a combination of really advanced thermal engineering, super efficient insulation for starters, MLI, multi-layer insulation.
Okay.
But the real game changer is the active cooling. They're using these things called pulse tube cryocoolers.
Cryocoolers,
Yeah.
like little refrigerators.
Kind of, yeah. Highly efficient mechanical cooling systems designed specifically to pump out any heat that manages to leak into the tank. Plus, clever tricks to manage the liquid in zero-G, like propellant settling, making sure the coolers are chilling the liquid, not just the gas above it, proving zero loss over 9 months. That's the key validation.
And if they crack that, if they show zero loss is actually practical in orbit, that just changes the whole economic picture for deep space, doesn't it?
Fundamentally, our research team's data confirms this, directly paves the way for that full-scale cryodock propellant depot they're planning for 2030.
The orbital gas station.
Exactly. Refueling in orbit is the absolute critical path for everything. NASA's Artemis program depends on it. Suddenly, the size of your rocket leaving Earth matters a bit less if you can top off the tank a few times in LEO before heading out to the Moon or Mars.
And speaking of Artemis, we saw more confirmation this week that SpaceX has to demonstrate Starship-to-Starship cryogenic transfer soon.
Yep, for their lunar lander contract.
That ability, transferring LOX and methane between starships, that's the linchpin for getting humans back to the Moon with Starship. So even though Landsat isn't Starship, its success kind of validates the whole principle, right? That handling cryos long-term in space is becoming an industrial problem, not just a physics experiment.
Exactly. It's moving from theory to engineering practice. Now, logistics isn't the only infrastructure getting built out. We're also seeing the first real orbital data centers take shape.
Starcloud 1.
Yep.
Launching with that powerhouse NVIDIA H100 GPU.
Which is huge. That's the first data center class chip in space. Why do you need that kind of computing power 250 miles up?
Well, it signals this shift from just basic satellite commanding to actual heavy-duty orbital computing.
Okay.
The H100 is built for accelerated computing, machine learning, running those big language models, exactly what you need for crunching massive amounts of Earth observation data in real time, or running complex weather models, or maybe even AI diagnostics on the space station itself.
Right.
Starcloud 1 is expected to offer something like 100 times the computing power of previous orbital systems.
Yeah.
This isn't just about running little experiments anymore. It's about building a real high-capacity digital economy in space.
And the economic case, the environmental case, it sounds almost too good to be true. The research team highlighting claims of, 10 times lower energy costs and emissions than data centers on Earth?
Yeah, it sounds counterintuitive, right? Launching all that hardware.
But the math apparently works out mainly because of two things. power generation and heat rejection.
Oh.
In orbit, especially certain orbits, you get almost constant sunlight for solar power. No day-night cycle like on Earth.
Continuous power.
Right. And crucially, getting rid of waste heat. On Earth, cooling data centers uses tons of water, tons of energy for chillers. In space, you just radiate the heat directly into the vacuum.
As infrared.
Exactly. Radiative cooling. It totally bypasses that huge terrestrial energy cost for cooling once the hardware is up there.
And they're already testing real applications.
Yep. Starcloud 1 is testing Google's Gemma open language model in orbit right now. And if this works, well, the projections are pretty wild.
Yeah.
The CEO suggested that maybe nearly all new data centers could be built in space within 10 years.
10 years? What?
Of course, that totally depends on Starship becoming fully operational. You need cheap, regular, heavy lift to make that happen.
Right, a big if. But still, mind-blowing potential. Okay, so we've got fuel depots, data centers. What about manufacturing?
Well, moving from digital to physical, we saw some really interesting progress in space biomanufacturing this week. Redwire, specifically. They seem to be shifting from just doing research in microgravity to actually figuring out commercially viable production.
This is the pharmaceutical crystal thing, right? The master template idea. Explain that, because that sounds like the key economic trick.
Right. So Redwire's work is focused on growing drug crystals in microgravity. On Earth, when crystals grow, gravity causes problems, convection currents in the liquid, sedimentation. It introduces flaws, impurities into the crystal structure in microgravity. None of that happens. You can grow these incredibly ordered, almost perfect crystals. And often these perfect crystals are more potent, more stable, just better drugs.
But making the entire world's supply of a drug in orbit would cost a fortune, right? Launch costs.
Exactly. That was the big economic hurdle. The genius idea, the master template concept, is realizing they don't have to make the final product in space. They just make a small amount of the perfect crystal in orbit, a high-value intermediate product. Then they bring that perfect crystal back down to Earth.
And use it as a seed.
Precisely. As a highly specific seed or template to guide the mass production process back on Earth, it allows the terrestrial factories to optimize their process to replicate that superior structure.
So you get the benefit of microgravity without the crippling cost of mass production in orbit.
Clever.
Very clever. It makes microgravity manufacturing a potentially scalable, realistic business.
Okay, so while Redwire is perfecting the product in orbit, we also need to talk about protecting the place itself. Orbital servicing, sustainability.
Active debris management. Yeah.
And the prime example this week is that high-stakes plan to save the Swift Observatory.
Yes, the Neil Gehrels Swift Observatory. This planned mission is a really critical, high-value test case for rapid response satellite servicing. NASA actually contracted Catalyst Space Technologies to launch a robotic spacecraft, a version of their Link vehicle, to go up and essentially rescue this $500 million observatory. And Swift wasn't designed for this, right? It's old, it doesn't have grappling fixtures, it's a non-cooperative target.
Exactly, which makes the mission incredibly difficult. Its orbit was decaying fast, mostly because the sun's been more active lately, puffing up Earth's atmosphere, creating more drag.
So without help, it was going to burn up.
Analysis showed a high chance of re-entry by late 2026. So the plan is to launch this robotic servicing vehicle, probably spring 2026, rendezvous with Swift, capture it carefully.
Gently.
Very gently, using smart, non-intrusive methods, and then just give it a nudge, raise its orbit to keep it operational for several more years.
It's basically a space tow truck for a very expensive, very delicate satellite.
Pretty much. A no room for error rescue, and it proves that these in-space logistics services, the tow trucks, the gas stations, are becoming a mature, necessary part of the market.
Right. It complements what companies like Astroscale are doing with debris removal and life extension, building the safety infrastructure for this new orbital economy.
Exactly. You need the rules of the road, and you need the roadside assistance.
And, you know, speaking of helping things along, if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled.
Yeah, it really does help new listeners find us. We appreciate it.
Okay, so we've got these massive technological shifts happening, the engines, the infrastructure, and now those changes are forcing equally massive strategic and commercial realignments back here on Earth.
Right. How the established players are scrambling to adapt.
Exactly. This section is really about how global space powers are responding to this disruptive pace set by new commercial space.
Starting with Europe, That industrial merger looked huge.
Monumental, really. Airbus, Leonardo, Thales,
Yeah.
signing that memorandum of understanding on October 23rd to merge their space divisions.
Yeah.
You're talking about creating this unified European space champion, valued at, what, over 10 billion euros? A powerhouse.
And this isn't just about corporate efficiency, is it? It feels like survival. That's exactly what it is. An industrial survival strategy. Historically, Europe's space industry was super fragmented.
National champions.
Right. A French satellite maker, a German supplier, an Italian rocket part. Often duplicating work, lacking scale, driving up costs. It was driven by national military interests, mostly, which got in the way of efficiency.
So this merger is a direct reaction to just being overwhelmed by the scale and cost effectiveness of, well, SpaceX mainly.
Primarily SpaceX, yeah. And also the big state-backed Chinese efforts. Europe simply couldn't afford to stay fragmented if it wanted to compete or even just maintain its own capabilities.
So the goal is strategic autonomy, being
Right.
able to build their own stuff reliably.
That's the explicit goal. Secure, comms, satellites, Earth observation, maybe habitats down the line, without needing to buy launchers or key components from the US or elsewhere. And the way they're structuring it is interesting.
How so?
It tries to solve that old fragmentation problem directly. Our research team noted it's being modeled explicitly on the MBDA missile consortium.
Ah, MBDA. What did they do right that this new space entity wants to copy?
MBDA managed to do two things that seem contradictory. First, it created one big company with enough scale to actually compete globally on cost and efficiency.
Okay.
But second, it kept mechanisms in place so that the really sensitive military R&D and production lines stayed under the sovereign control of France, Italy, Germany, the UK, etc.
Ah, so you get market competitiveness and national security.
That's the balance. And this new European space giant is trying to pull off the same trick. Scale up the commercial side, but keep the strategic bits ring-fenced where needed. It's expected to be up and running by 2027, apparently.
Okay, so while Europe is consolidating to compete, Russia seems to be making a really interesting calculation about cooperation versus going it alone.
Yeah, with their planned orbital station, ROS Roscosmos announced a pretty significant strategic U-turn this week. They've decided to put ROS into the exact same orbital inclination as the ISS. 51.6 degrees.
That is a big shift. Why? What was the old plan?
The original plan was a near-polar orbit.
Right. Which would give them great coverage over Russia itself.
Yeah.
For national security, observation.
Exactly. A clear, important national security goal. This new decision sacrifices that comprehensive Russian coverage.
So they're giving up a military objective. Why?
It seems like a stark geopolitical calculation. They're trading that national security coverage for staying plugged into the international human spaceflight logistics network.
Ah, because everything is set up for that 51.6 degrees.
A whole ecosystem. Soyuz launches, Dragon, Starliner, ground control. It's all optimized for the ISS inclination. By putting ROS there, too, Roscosmos makes sure that future vehicles, whether they're from international partners or, maybe more importantly, commercial companies, can actually get to their station easily. It avoids needing totally new launch plans, new procedures. It's basically a pragmatic signal saying, okay, after the ISS, we still want to be part of the main network.
So access to the global orbital highway is strategically more valuable than maximum eyes on their own territory.
It appears so. It suggests they see staying integrated as more beneficial than pursuing a purely isolated national path, which would have kind of walled them off logistically.
Interesting. Okay, we can't really talk about operational tempo and realignment without mentioning the benchmark, right?
Yeah.
SpaceX.
You really can't. The pace is just staggering. The numbers don't lie. This week, SpaceX hit its 134th orbital mission for 2025.
134. And that matches their entire total for 2024.
Yep. The research team confirmed that, matched the whole previous year's total, and there are still over 2 months left in 2025.
Wow.
That kind of factory-like cadence just fundamentally resets the economics of space access for everyone else on the planet.
And we saw their flexibility, too, with that SpainSat NG-2 launch.
Right. The secure communications satellite.
They used a Falcon 9 booster, but they intentionally didn't recover it.
Correct. They expended the booster. Threw it away, essentially.
To squeeze out more performance.
Exactly. To maximize performance and lift that heavy satellite into a really high-energy orbit, exactly where the customer needed it. It shows the trade-off reusability allows. Usually you want to save the booster for cost. But sometimes the mission physics demand every last bit of push. Expending it lets them offer maximum lift when needed, trading reusability for performance.
Meanwhile, Starship development just keeps churning. They had the 11th integrated flight test.
Successful, yeah. That was the final V2 variant test.
And now they're pivoting straight to V3 with the lunar and Mars upgrades.
That's the plan. That rapid iteration, throwing hardware at the problem, it forces everyone, regulators included, to just adapt to this new reality of how quickly things can change.
Speaking of regulators, the FCC got involved this week too. Declared October Space Month.
Yeah, and released some proposals to modernize their rules.
Yeah.
Which is badly needed.
Might be a huge job, right? Space isn't just big GEO satellites anymore. It's CubeSats, mega constellations, those orbital data centers.
Exactly. The FCC's move is a really crucial acknowledgement that the new space economy is here, and it's complex. They want to replace the old Part 25 rules.
Which were written for, like, the 70s and 80s?
Pretty much. Slow, monolithic satellites. They want to replace it with a new, streamlined Part 100, Space and Earth Station Services.
Okay.
The big shift is moving away from telling companies how to design their satellite to just setting performance standards. Basically, prove your system won't interfere with others, and we care less about the exact design.
That makes sense. And the most interesting bit, maybe, was that new license type they proposed. VTSS.
Variable Trajectory Space System. Yeah, that's fascinating.
What's that for? Things that move around.
Exactly. It's designed specifically for stuff that doesn't fit the old stationary satellite box. Think about building things in space assembly, manufacturing, docking, servicing, even lunar operations.
Because the spacecraft is constantly changing shape, mass, trajectory.
Right. The old rules kind of assumed a static object in a fixed orbit. VTSS acknowledges that the future involves dynamic stuff, construction, servicing, depots, where the operational thing changes during the mission.
So regulation is finally trying to catch up with, and even enable, this much more complex space economy.
Trying to, yeah. It's a big step.
Okay. So we got better engines, orbital infrastructure taking shape, global powers repositioning. What does it all enable? Beyond the market moves, maybe the best illustration is that amazing science happening right now, millions of miles away.
You mean 3 IELTS?
Exactly. The interstellar visitor.
Yeah, the third known object to wander into our solar system from interstellar space. It's become this incredible example of opportunistic science and a real test of our modern mission agility.
Especially for NASA's deep space probes.
The stakes here are just incredibly high. NASA's Europa Clipper probe.
Which is on its way to Jupiter, right? That's its main job.
Exactly. But it's being retasked, diverted slightly, for an unplanned flyby of 3 IELTS, specifically to fly through and sample the comet's ion tail.
Wow. When is that happening?
Between October 30th and November 6th, it's an immense engineering challenge.
Because this is a chance to grab actual material from another's star system.
Pristine material, yeah.
Yeah.
Scientifically, it's priceless. Normally, doing something like this would take a dedicated mission, planned years, maybe a decade in advance, costing billions.
Right.
Being able to pull this off now, opportunistically, depends entirely on advanced mission adaptability. Clipper wasn't designed to chase random interstellar comets.
No.
Its path, its fuel budget, all set for Jupiter. Doing this means burning precious maneuvering fuel, recalculating its whole trajectory based on these fleeting observations of ATLS, rewriting commands on the fly.
And the software to do that must be incredible. The research team mentioned something called Tailcatcher.
Yeah, that's apparently one of the key algorithms. It predicts where the comet's ion tail will be with enough accuracy for Clipper to basically thread the needle, aiming its instruments right through the densest part.
That level of prediction, precision, autonomy, doing an unplanned high-speed flyby of something that isn't even from our solar system.
It's a testament to how far predictive software and deep space navigation and communication have come. It shows this operational maturity that just wasn't there even 10 years ago. It turns a mission from just executing a pre-planned script into an agile, real-time discovery machine.
And the early science findings already show why this is so important. New images showed a huge jet of gas and dust coming off it.
A giant jet streaming towards the sun, yeah. And the composition they're seeing already. Fascinating.
What have they found?
High levels of carbon dioxide, lots of water ice, which is maybe expected, but also cyanide gas, and even atomic nickel vapor.
Nickel vapor. That sounds unusual for a comet.
It is. The overall mix seems noticeably different from the comets born way out in our own Oort cloud. So getting an actual sample of this stuff, it's an unprecedented window into the chemistry of how stars and planets form somewhere else entirely.
It's literally sampling an alien world's building blocks.
Pretty much, yeah.
But inevitably, whenever something this amazing happens, an interstellar visitor, it also kicks up a lot of noise. Right? The challenge of information integrity.
Oh, absolutely. It's almost guaranteed now. The research team definitely noted the wave of online speculation, misinformation.
Claims it's artificial conspiracy theories.
The usual suspects.
Yeah.
And it highlights this growing challenge for NASA, for ES, for anyone doing cutting-edge space science. You have the slow, careful, rigorous process of scientific verification, colliding with the public's instant demand for answers, for wonder, for mystery. Managing that gap, separating the real signal from the overwhelming noise, is now a critical part of running any major space mission. Communicating the real science effectively is harder than ever.
Yeah, navigating the excitement without feeding the frenzy. Tricky balance.
Very tricky. Hashtag tag outro. So if we try to pull all these threads together from this incredibly busy week, I think 3 big themes really stand out. Themes that define where the beyond Earth economy is heading. First, just efficiency. That RDRE investment, the work on cryogenic refueling, these aren't small tweaks. They're fundamentally changing the economics of getting around in space. Reducing costs, reducing complexity, making sustained operations actually possible.
Right. Second, I'd say scale. You see it with SpaceX just churning out launches like a factory. You've seen in that huge European merger. It's not just business news. It's a global drive to build the massive industrial capacity needed to support permanent off-world activity.
Absolutely. And third, sustainability. The FCC trying to modernize rules, that practical demonstration of robotic servicing with the swift rescue, the ongoing work on debris management. It's all about establishing the rules of the road, making sure ELIO and Cis-Lunar space don't become unusable Wild Wests, creating a framework for safe, sustainable traffic.
Yeah, those 3 really capture it. And maybe the biggest takeaway, looking at what our research team pulled together, it's that these things happening this week, these specific technologies, these industrial structures, they aren't just incremental steps.
No.
They feel like the permanent cornerstones, the foundations that will decide who leads and who lags in this beyond Earth economy for, well, the rest of the century probably.
I think that's right. These are foundational shifts.
So just one final thought to leave you with. Consider that projection we talked about earlier, about orbital data centers. The idea that within just a decade, almost all new data centers might be built in space. If anything close to that happens, what does it do to geopolitics? Does the strategic importance shift from controlling sea lanes or oil fields or even terrestrial land to controlling orbital pathways, access to specific inclinations, low latency communication points?
That's a fascinating question.
That potential shift in value from the ground beneath our feet to the orbital mechanics above our heads, that feels like something that's going to drive policy and conflict for decades. Something to chew on.
Definitely food for thought.
We always love hearing your thoughts, too. Whether you're watching on YouTube or listening on your favorite podcast app, please leave a comment. Let us know what you think about this week's breakthroughs in space.
Yeah, please do. And thank you for diving deep with us here on Tomorrow Unveiled.
Thank you for joining Tomorrow Unveiled.